Hey folks. Okay, well let's see. We got as far as looking at a sort of simple tree walking routine that would go through and do code generation for basic expressions. So we were looking at just sort of binary expressions on kind of numeric literals and variables, and just getting it to output the code to load the variables into registers, perform the operation, and stick the result in a register. So even from the point of view of keeping, just sort of the primitive side of things going here, we still need to think about what to do with that tree walking routine in terms of handling function calls, in terms of dealing with type conversions where we've got operations with mixed data types in the operands, how to deal with things like assignment statements, whether there's special issues that we have to look at there, and then get into the conditional branching side of things, because of course that's going to be crucial when it comes time to dealing with loops and if statements and switches and all that sort of thing. So these are some of the things that I want to touch on in this session. So let's see how we go here. Just kind of taking things in the order listed. Looking at function calls, we talked in the sort of intermediate representation stage about the idea that the compiler is going to need to generate the assembly language code to divvy up responsibilities between the caller and the callee. So saving the current registers, setting up space for return values, setting up space for parameters, getting them in the stack, for instance, carrying out the actual call, and then setting up the local variable space, getting that initialized, and undoing all this process at the end. So that should actually be relatively seamless in the instruction sequence that we were looking at from our code walker, right? It was getting to the point of saying, well, we need the next value to use, so now we generate the code to make that call. It winds up, generating the code to make the return, and at the end of all that, the value winds up in a register, which is what we wanted. So for the most part, that should fit in reasonably seamlessly. One of the places where we have to think about the issues is where we talked about the optimization ideas. So if we were thinking about the compiler sort of rearranging some of the code so that it can group similar subtrees, group similar computations, and reuse the results from those, the possibility that a function has side effects kind of messes with that idea. If we've got something like a plus b minus the result of some function call and then another a plus b, we can't necessarily reuse that second a plus b as the same expression tree, if you like, if there's a possibility that that function call in the middle altered a or b. So in this case, if it's passing a as a parameter, unless that's passed by value, there's a possibility for a side effect there. If either of a or b are global, then there's a possibility of a side effect there. If there's a possibility that f calls a function that somehow impacts a or b, there's possibility of side effects there. So the compiler has to be really wary of performing certain optimizations if there's a function call embedded in the middle of an expression. So that is one thing to keep in mind. We've got the idea of mixed type operations. So if we think of something like a plus b, where maybe they could be ints or floats, for instance, if one of them's an int and one of them's a float, then we have to figure out what kind of operation to perform. Again, typically our compiler is going to have a table where it looks this up and says, okay, if I've got an int and a float, what do I do? And it's going to say, okay, if you've got an int and a float, convert the int to a float. So at this point, it's going to have to, as part of that, either as part of the tree walker or as part of the output routine that it called, it's going to have to generate the appropriate conversion to take the value that's in the register holding the a value and calculate a floating point equivalent and put that in a register and use that other register as the expression that we're working with here. So that has to be embedded as well. But again, that's reasonably mechanical, right? There's not a complex set of operations there. It's just do a type check. So maybe you've got a function that performs the type check. If it says something's got to be converted, then we embed the code to convert from current type to needed type. And so again, this can be relatively mechanically added to our code generation. Assignment operations we should think about, since they are actually going to be changing the value of a variable. So we have to make sure that, if we've got that variable stored in a register someplace, it's updating the correct register, and that eventually is going to get written back to the right place in memory. If the variable is currently in memory, then we've got to figure out a way to get the assigned value into the right memory location. So whatever sequence of code statements we have to generate to accomplish that has to take place with our assignment operation. Now, again, for the most part, the convention is to do these things from right to left, so that if you've got a chain like x is equal to y is equal to z, then you start from the left-hand side, evaluate z, assign the value to y, take the result of that, assign the value to x. It doesn't have to be that way, but in a lot of circumstances that makes the most sense. Right? In theory, we could go through and carry out the assign y to x, and then go through and assign z to y, and etc., etc., etc. So, could be done either way. Again, typical approach is to say evaluate the right-hand side, assign to the left-hand side. That means that our assignment operator has to be pretty low precedence so that the rest of the evaluation takes place first. You do have to think about, possibly the appropriate conversions, just like with our other operations. Right? If we're assigning an int to a float, think about the appropriate conversion. If we're thinking about a float to an int, think about the appropriate conversion. If there's a type mismatch, again, we've got to perform our type checking and generate the errors back wherever we are generating our errors. And of course, for languages that support more complex assignment operations, if you've got things like a plus equals where it adds y to x rather than just assigning y to x, then that might involve a couple of different operations. But again, if you're modeling that kind of mentally as, add x and y and then assign the result to x, it's a relatively straightforward sequence still. And of course, there's operations like plus plus or minus minus, which, again, if you're thinking about them, you're performing an arithmetic operation on the current value and assigning the result. Boolean operations is where things get a little interesting, so we'll spend a bit of time on this one. Again, the purpose of having a Boolean operation is to figure out a true or false value so that you can then later on say, okay, well, if this is true, do blah, and if it's false, do something different. So usually these are closely related to the idea of some kind of branching instructions. Right? You've got condition checking and branching orchestrated in some way or another. In terms of where these things fit in the great precedence scheme, it's not universal, but it's pretty common to use an approach something like this, where you say, okay, well, we'll make the OR the lowest precedence in the sequence shown here, then the AND is higher precedence, then we'll have the comparison operations at a higher precedence than that, so that we can actually do things like say, if A is less than B and B is less than C. And it's not going to work like this in C. I'll let you go through and play with the precedence operations in C and see what happens if you... pardon me. This is fine if you just do A is less than B and C. Never mind. I'm babbling and losing my mind. Yeah, so we'll go through and follow a sequence like this so that you can say things like this and have reasonable behavior result, where it's going to perform the two comparisons first and then take the logical AND of the results. So you get the result that hopefully one would expect. Usually negation is at a higher precedence than that, and we've got our arithmetic operations in between. Again, so that if you've got something like A is less than B plus C, and B is less than C, or some such thing, that's probably not much of a sensible operation, but again, it will go through and perform the math first, then do the comparison, then do the logical AND. Right? So that it's a reasonably sensible orchestration. You do have to be aware of whether short-circuiting is in use or not, right? The idea that true or X is true. So in theory, you don't even need to bother evaluating X, and that's the essence of short-circuiting. If you see true or and whatever, you ignore the whatever and just say, it's true, short circuit. Or false and whatever is false, so you ignore the whatever. If you evaluate the left-hand side to false, then you just say, forget it, I'm not bothering with the rest, the result is false. Which is fine, unless that other portion includes something like a function call or an operation that has a side effect, in which case, with short circuiting, there's no side effect. Without short circuiting, there is a side effect. So you have to be sure that you understand what the source language expected and what the target language does, so that when you're translating between the two of them, you get the behavior that you actually want. And again, you can do similar things with some other kinds of operations. If you have something like 0 multiplied by x, you know it's going to be 0. You don't need to know what the x is. But again, you want to be aware of what your source language expects and what your target language does to make sure you get the behavior you want. All right, in terms of translating our high-level language statements to assembly language, again, you need to know what's provided at the assembly language level. What are the test and branch operations, and how are they best utilized to get the effect that you want? So we'll look at 4 different schemes that are kind of based on what the given language provides us with. So one is based just on condition codes. One is based on condition codes plus the availability of a conditional move. One of them is based on a Boolean comparison, and one is based on predicated execution, where we ignore a whole lot of this other stuff. So we'll take a look at each of these 4 schemes, and again, each of the 4 of them is going to be good in some situations and not very good in others compared to the other schemes. So looking at the 4 of these in sequence, the basic condition codes approach. So this assumes that we've got some kind of generic compare operation where we give it 2 registers. So we say compare R1 and R2 and update the contents of some kind of status register. So that status register will have different combinations of flags so that we can look at it later and we can tell whether R1 was less than R2, whether it was equal to R2, whether it was greater than R2, whether it was less than or equal to, greater than or equal to, not equal. So we'll set a variety of flags in whatever condition register you give it. So the idea is we perform this generic comparison, and then our branch operations say, okay, I'm going to have a different branch operation for each of the different kinds of things I want to look at. I'll have a branch operation for less than, a branch operation for less than or equal to, a branch operation for greater than, or at least different subsets of these things. So you give your branch the specific kind of branching comparison you want to look at, give it the condition register, and then give it, say, 2 different labels. And if the condition checks true, so if R1 was actually less than R2, for instance, then we'll jump to label 1, otherwise we'll jump to label 2. Now again, there are a ton of different variations on this kind of idea across different assembly languages, but this is the notion. We set a bunch of condition flags, we have a specialized branch operation that looks at those flags and says yes or no, am I going to branch, or am I going to branch to this or to that? So that's the condition codes approach. The conditional move is basically saying we've got that, plus we'll have a specialized move in addition to the specialized branches. So we'll have a move that says, look at the condition, and if this condition is true, so a move less than, for instance, so if R1 is less than R2, then we'll have 2 different data values, and we'll move one of the 2 of them into a destination. So for instance, if R1 is less than R2, we'll move, or pardon me, in this case, if R1 is less than R2, then we'll move R1 into R5, and otherwise we'll move R2 into R5. So these are our 2 possible data values. We're picking one of them based on the result of the move operation we've picked, or the move condition we've picked, and the condition register that we're checking. So it's basically just adding one more fancy operation to our suite of branching operations. The Boolean compare takes a different approach. We drop the idea of condition code registers, and instead we have a kind of generic branch operation that looks at a register and says, if it's true, I'm going to branch to one label. If it's false, I'll branch to a different one. So in this case, it's the compare operations that are specialized. So we'll have a compare less than, a compare greater than, a compare not equal, a compare equal, that kind of idea. We give it the 2 registers, and we give it a register to put the result. And it's going to do the comparison that we asked for and put a true-false result in the target register. So if we say compare less than and R1 is less than R2, it puts true in R3, otherwise it puts false in R3. Then our basic branch operation just says, okay, you give me a register and two labels, and if the register contains true, I'll branch to the first one, otherwise I'll branch to the second one. Again, just a different way of orchestrating things based on whether we've got a generic branch and specialized compares, as opposed to our condition code one, which had a generic compare and specialized branches. Same idea, we're just doing things the other way around. The other one, the predicated execution, is the idea of having a kind of combined operation here where we have essentially an if test and an instruction, and says, if this thing is true, do the instruction. So the idea is we take this operation and it's got a register as one operand, and then it's got a complete instruction as another operand. If the register contains true, then do the instruction, otherwise don't. Right, so this is kind of like saying, if R1 is true, then add R2 and R3 and put the results in R4. And you can imagine that if you've got this kind of more complex instruction, it's much closer to the kind of higher level logic that we're thinking of. So you can picture something like this reducing the number of instructions that we need to do certain things. All right, so let's take a look at an example with all four of those different ideas just to kind of get a feel for what they might look like in practice. So here's our little chunk of high-level code that we want to try and implement. So if a is less than or equal to b, I'm going to say x is assigned y plus z. Otherwise, I'm going to say x is assigned I minus j. So we've just got a couple of different expressions that we're going to carry out and one test. And again, it's just looking at the different way things are going to look based on the kind of operations we've got. So that condition code version where we've got a generic compare and specialized branches, say, okay, well, compare the register that's got A in it with the register that's got B in it and set a condition code register. And then do our specialized branch, our branch less than or equal to, right? Look at the status register and go to either L1 or L2. In L1, we do the first add, the x is assigned y plus z, and then we skip over the second part, right? We jump past it to whatever's next in the program. And otherwise, the L2 section performs the subtraction to assign the other result to x. And again, plows on with the rest of the program. So, nice and straightforward. If we were going to add in the conditional move idea, where now we've got our comparison, we've got our branches, but we've also got specialized move instructions, then maybe we take a different approach. We don't have to, this isn't a required way to do it. Again, there's lots of different approaches, but maybe what we'll try here is say, okay, let's compare the two of them. Let's do the two different computations. So we'll compute the result of y plus z and stick that in one register, and compute the result of I minus j and stick that in another register. And then we'll use the move, our specialized move, to say, okay, if that comparison said A was less than B, then I'll move the R1 answer into X, and otherwise I'll move the R2 answer into X. Now again, this one is maybe a shorter instruction sequence, fewer jumps, but we're going through and we're doing both comparisons no matter what, instead of only doing both arithmetic operations no matter what. So just another way of looking at things. The Boolean compare was the one where we had the specialized compare and a generic branch. So this pretty much looks like the first one, except that we use the specialized comparison and then the generic branch. So do the less than or equal to comparison on A and B, stick the result in register R1, and based on what's in R1, branch to either L1 or L2. Other than that, it should be pretty much the same. And then for that final one, the predicated execution, we'll figure out if A is less than or equal to B. We'll figure out that, and we'll figure out its complement. So if A is less than or equal to B, we do want to do the first instruction, the addition. We don't want to do the second instruction. And the other way around. If A is greater than B, then we don't want to do the add. We do want to do the subtraction. So I'm just going to throw in two of these predicated tests saying, okay, well, We'll make R2 the opposite of R1. And so if R1 is true, we'll do the add and stick the result in X. And if R2 is true, we'll do the subtract and stick the result in X. And since they're opposites, only one of the two of them will be true. Again, different approaches. They all come up with the same result in the end. And it's just based on whatever particular features the target architecture provides us with. All right, that seems like a good place to leave that for now. We'll pick up with more fun next time around.